Electric field due to uniformly charged spherical shell or solid conducting sphere. This is a uniformly charged spherical shell. The whole charge remains on the outer surface. Remember, no charge available in the inner surface. This is uniformly charged solid conducting sphere. In this case, the whole charge remains on the surface because it is a conductor. The charges repel each other, they move away from each other, then they reside only on the surface. But in the case of non-conducting solid sphere, the charges localized inside the non-conducting sphere. These two cases can be treated as one because they produce the same electric pattern. Consider a uniformly charged spherical shell or solid conducting sphere of radius r carrying a total charge q. This diagram, you can take it as a solid conducting sphere or a spherical shell. Case 1. At a point outside the shell, small r is greater than capital R. A is a point outside the shell which is at a distance small r. A Gaussian surface is being considered. The surface of the Gaussian sphere passes through the point A. At all points on this Gaussian surface, the electric field is perpendicular to the surface. Draw a Gaussian sphere with radius small r through A. Inside this Gaussian surface, the net charge is q. Assume it is concentrated at the center O. By Gauss law, Es equals q divided by epsilon naught. Here S is the surface area of a Gaussian surface. So it is 4 pi small r square. Substituting and finding the value of electric field E equals 1 by 4 pi epsilon naught q by r square. Now, second case, at a point on the shell, small r equals capital R. Here you have a point B just on the solid or spherical shell. Now, a Gaussian surface is passing through this point B. I have made that sphere little bigger to be visible. At this point, not only at this point B, at all point on the Gaussian surface, the electric field is perpendicular to the surface. Draw a Gaussian sphere with radius capital R through B. Inside this Gaussian surface, the net charge is q. Assume it is concentrated at the center O. By Gauss law, Es equals q divided by epsilon naught, and the S is the surface area of this Gaussian sphere, which is equal to 4 pi capital R square, and finding the value of electric field E equals 1 by 4 pi epsilon naught q by capital R square. Now, case 3. At a point inside the shell where small r is less than capital R. Now, consider a point C. Now, we have to imagine a Gaussian sphere, the surface of the Gaussian sphere passing through this point C. Draw a Gaussian sphere with radius r through C. Inside this Gaussian surface, the net charge is 0 because all the charges available only on the surface of the shell which is outside this Gaussian surface. So Es equals q by epsilon naught, q is 0. Therefore, the electric field inside the shell or solid conducting sphere is 0. Let us have all these three cases in a graph. Case C, at a point inside the shell where electric field is 0. So this has been represented from O to R with the red line, where electric field inside the sphere, solid sphere or spherical shell is 0. Then at a point on the shell R equal to capital R, where we have the maximum electric field, E equals 1 by 4 pi epsilon naught Q by R square. So at a point R on the distance axis, we have the maximum electric field E equals 1 by 4 pi epsilon naught Q by R square. Now case A, at a point outside the shell, E equals 1 by 4 pi epsilon naught Q by small r square. This is represented here by a line, a curve, E proportional to 1 by R square. Thank you.